In question 3, we have a helicopter rising vertically at a constant velocity initially of 7 meters per second. When the helicopter is at a height of 90 meters above the ground, that will be our initial height, the technician accidentally drops a spanner out of the window. Let's spend some time taking a look at this particular question, analyzing the graph before moving on to the actual questions asked. The first thing to note is, and this may seem trivial or obvious, it's a velocity time graph. So don't get confused and start thinking that it's a displacement time graph. It is a velocity time graph. Over here, we have the initial velocity of the spanner. We're given that as 7 meters per second, and you can see that it is a positive velocity. And that's because initially your helicopter is rising vertically. So clearly this is consistent with choosing up as your positive direction. So this entire region of your velocity time graph over here, you can see it being circled in red at the moment, that is a region in which your velocity is positive. So clearly the spanner is still moving up. The reason your spanner is still rising is due to Newton's first law of motion and due to its own inertia. At this point, labeled r on your time axis, the velocity is 0, and that's because every point on your time axis has a 0 velocity. If the velocity is 0, your object is not currently moving. And then this region over here corresponds to a negative velocity because it lies below the time axis. A negative velocity in this particular context means your object is moving down. In summary, your object is moving up in this region, it is momentarily at rest over here, and it is moving down towards the ground in this region. Now let's take a look at the actual questions asked. Because your object is initially moving up, it must have kinetic energy due to its motion, and because it starts out above the ground, it must initially have gravitational potential energy. In order to get 2 marks here, you did need to list both types of energy. The slope or gradient of the graph, the marking is quite strict on this one. You need to realize that in general for a velocity time graph, it gives you the acceleration of the graph. That wasn't enough to get you your 1 mark. You needed to read into it and be a little bit more specific here. Not only is it the acceleration of a velocity time graph, your gradient in this context, because we're working in free fall and with vertical projectile motion, is actually your gravitational acceleration, or negative 9.8 meters per second squared. Question 3.3, the point on the path of the spanner corresponding to time r. We've already spoken about time r being the point at which your spanner is momentarily at rest, and your spanner is momentarily at rest with a 0 velocity at a point of its maximum height. In question 3.4, we're asked to use an equation of motion to calculate the time r on the time axis. That's your time at which your spanner is momentarily at rest. The information we have is this initial velocity of 7 meters per second. We know that the gravitational acceleration is negative 9.8 meters per second squared, and this is consistent with a direction convention of choosing up as positive. Obviously you could have chosen down as positive as well. And the other piece of information we have is that at point r, at the point of maximum height, your final velocity is 0. So a sensible choice of equation here is this one, the one that relates final velocity, initial velocity, acceleration, and time. And the time in this particular case is r, which is the variable that we are looking for. Writing down the formula gets you 1 mark. Substituting directly into the formula gets you another mark. And then working out that formula and solving for r, the time that we're looking for, together with the unit, the appropriate unit here is seconds, gets you your 3rd mark. In question 3.5, again you're asked to use an equation of motion, this time to find the magnitude of the velocity of the spanner as it reaches the ground. We know that the spanner initially rises, it reaches a maximum height, and then it starts falling, and at some point it's going to reach the ground, and we're looking for the magnitude of the velocity at that particular point. Known information we have, we still know that the acceleration due to gravity is negative 9.8. That's a known. We know that the initial velocity of the spanner was positive 7 meters per second. This is still using a direction convention of up as positive. The other piece of information we have here is that your spanner started out at a height of 90 meters. If it has fallen to the ground, it means that overall it has dropped by 90 meters. Its height has decreased by 90 meters, and thus delta y needs to be negative 90. Substituting in negative 9.8, negative 90, and 7 into this formula, the equation of motion relating final velocity, initial velocity, acceleration, and your displacement, in this case a vertical displacement, gives us a relationship that allows us to find the final velocity. 1 mark for the formula, a mark for all your substitutions, and once you've found the final velocity of 42.58, correctly rounded to 2 decimal places, with a unit of meters per second, that gets you your 3rd mark, the answer with the unit. Question 3.6, you needed to pay attention to the instruction in bold. Use the graph. Okay? It means you couldn't use an equation of motion. You had to take a look at the graph, and you had to calculate the maximum height reached by the spanner using the graph. Now, with interpreting graphs of motion, the only graph work you can really do is either calculate the area underneath a graph, or you can calculate the gradient of a graph. In this particular graph, it's a velocity time graph. The gradient corresponds to the acceleration. We've already used that. The area underneath a velocity time graph, that corresponds to the displacement. So in order to calculate the maximum height, what you really need to do is calculate the area underneath the graph by the time it reaches that maximum height. Pulling in the graph we need, the relevant area you can see shaded over here. The area for a triangle is half base times height. In this particular case, the base is time r that we've just found, and the height is the initial speed of 7 meters per second. Performing the calculation tells us that delta y, or the vertical displacement, was 2.5 meters. This gets you 3 out of your 4 marks. To get the 4th mark, you need to realize that the maximum height isn't actually this 2.5 meters. You need to take your initial height of 90 meters, add the change in height, or the vertical displacement of 2.5 meters, to get the total final height, or maximum y value, of 92.5 meters. With the displacement time graph that you were asked to draw in question 3.7, there were 2 options in terms of which you chose as your 0 reference height. And by that, we mean the height that you treat as h equals 0. In this particular case, we've chosen the ground as the 0 reference height, in which case you treat the ground as 0 and anything above the ground as a positive height. In this particular case then, using this reference, 90 meters is your initial height, and you can see that here in the graph. When t equals 0, the intercept with the y-axis is 90. Your spanner it rises, slowing down, and eventually hitting a maximum height that we've just found of 92.5 meters. This is the turning point. Here you see a 0 gradient. The tangent line would be horizontal, and the velocity is 0. That corresponds with time r, which we found at 0.71 seconds on the time axis. From this point forward, the spanner starts to fall. Initially it falls slowly, and as gravity acts for longer and longer, it speeds up and eventually hits the ground at a time here which we didn't need to calculate and we didn't need to show. The other possibility would be treating the point of release as your zero reference height, in which case your object starts at a zero reference point. It starts at 0, so the point at which you released it is the 0 point. It rises up 2.5 meters, so it eventually reaches a maximum height, which according to this reference is 2.5 meters, and this is the height found in the previous question, and that happens at the same time r 0.71 seconds. From this point forward, your spanner starts to fall, and eventually it gets back to the 0 reference height, which is the same height at which you released it. The spanner then continues to fall, and it actually falls below your reference height until it hits the ground. This is a little bit more complicated, and it's actually easier to treat it in the previous way, but it is possible to treat it this way correctly.